Recording, and share my screen once I get to the tab with my slides on it. All right. So the way I'm going to structure this presentation is you're going to get all the math up front, and as your brains get tired, the presentation will become increasingly less technical. So if you feel like you're struggling at the beginning, I try to make it simple and accessible. But if you feel like you're struggling at the beginning, don't worry, it will get easier. Um, okay. Without further ado, we can get started. Can everyone see my screen?
Yep.
Okay. So today we're going to be talking about the R1 paper, which I think by nature of like what it does isn't actually a very innovative paper, as I found after reading essentially all of the many preliminaries that led to this thing or skimming them. Almost all of these advancements were made in previous works, and this paper just puts them all together. The reason for the massive amount of hype behind this thing is essentially that it's a system with a really great interface in the same way like GPT 3.5 was, but like as a paper, this paper does not contain many of the advancements you see, and to get those, you need to read other things. But I'll try to give you an overview of a bunch of different things that come along here. By the way, if at any point anyone has any questions, feel free to interrupt. I'm more than happy to try to answer them to the best of my ability. Okay, here's what we're going to do. We're going to start with GRPO because it is the most mathematical thing in this paper. Then we're going to try to understand their training pipeline and what they do architecturally that either the big companies didn't or the big companies did and didn't report because everything is proprietary today. And then we're going to talk a little bit about DeepSeek as a company and sort of like the implications of all of this. Um, okay. So what did DeepSeek do and like why do we care? Like the really high level overview is DeepSeek is a Chinese startup that's sort of funded by this larger Chinese AI trading fund called Highflyer. They're essentially like a branch off that's managed by the same CEO, in order to, as they state their goal, essentially achieve artificial general intelligence. Um, what their real goal is, I'm not quite sure. But they essentially built a model for way, way cheaper that in some very specific areas performs with the likes of O1 and certainly exceeds like models like GPT-4o at a pretty major fraction of the cost. It's almost an order of magnitude cheaper. Um, Many people say that the price difference is like $1 billion for training as opposed to a 6 million training run for DeepSeek. We'll see that that's not true, but you still reach an order of magnitude efficiency difference with improved performance and a lot of methods that are very, very simple and not particularly elegant, but actually seem to work. Here I have an overview of the R1 pipeline. They actually train two models. One is called R10, where they don't do half of this stuff, and one that's called R1 that's like somewhat better than R10. I'm going to be talking mostly about R1, but if you have any questions about R10, I'm more than happy to answer them. Essentially, the overview of the pipeline here is that they're just going to alternate fine tuning and something called GRPO, which we're going to get to now. So I'm gonna I'm not gonna start at the beginning of reinforcement learning. I'm going to assume that people have seen like policy iteration. If you haven't, you can think of policy iteration as like a black box that solves like a system of equations in order to, and almost like solves a system of equations iteratively in order to find some reasonable way to like reasonable estimations of how valuable certain actions are. Now, the problem with policy iteration and sort of these very naturally discrete methods is that you have to take the maximum over a large set of actions. If we're talking about a more continuous policy, that quickly becomes intractable. And we do what everyone does in neural network land, which is gradient descent, or I guess in the case of reinforcement learning, it's usually the inverse, gradient ascent. So you have this model pi, and that's usually like in NLP, that's usually your neural network, right? Like you have your model pi and it's parameterized, meaning like it has parameters, theta, and it predicts like the next action, A, given the state you're in, S. S is usually like the words which have come before, and actions in NLP is like the next token you predict. Now, the cool advancement of policy gradients is like the policy gradient theorem, where essentially what we had before was that you would take, if you took the gradient, you need to both account for the frequency with which states appear and the relative value they provide. The frequency is going to be this like d pi of s, and the value they provide is like the q pi of sa times like the probability they happen. So when you are taking a gradient relative to how often states appear, you kind of need to iterate for a very long time across the states in order to figure out how often each one of them appears. And taking the gradient relative to this function is a really complicated thing. All the gradient policy theorem does is through like a lot of like recursive math essentially show that you don't actually need to compute the gradient relative to that thing. And you can just compute like the gradient relative to pi, which once again is the neural network directly. So this is like classic good old gradient descent that you are able to do in reinforcement learning, essentially, in order to optimize a policy. And once again, a policy is like the set of actions you want to take given the state you're at. So the next word you predict, given the words you've predicted so far. Is everyone with me up to here? Okay. I'll keep talking and assume that I'll be interrupted if something uh, problematic pops up. So with now I'm going to explain two vocabulary terms, and those are going to be the actor and the critic. The actor is like a very like simple term concept. It's like the neural network that essentially produces the next token one at a time. It's parameterized by like the neural network's parameters, and it uses like that neural network function, like it's an input plugged into a neural network to predict the following output. So that's your actor. Once you have sort of essentially converged to a set of parameters, you can estimate how much better your actions are than the expected value from that state. So Q of STAT is essentially the quality of like the total value you assume given you start at a certain state and take a certain action. I want to make a note that this is long-term reward. So this is like the expected reward across an entire sequence of tokens. So like let's say you start with the sentence I like, and then your next word is uh, pizza. Your sort of the quality of that action does not just consider the next word was pizza. It considers like the expected reward across the rest of the sentence. So maybe the rest of the sentence is and cheese or something like that. Then those rewards are sort of a part of Q. You sort of try to predict what the totality of your future reward will be, given you took one step forward, given you essentially attempted a single action. And this AT, this advantage, is essentially a metric on how much better off this action made you. So you took an action, you were at state ST, you took an action AT, you're basically computing how much better off was I than if I'd just taken any random action, which is why V is not a function of AT. It's just a function of the state. It's like once again, how much better off am I than just taking a random action? Now, there's a certain problem with this, which is where we can essentially have two approaches. The problem is that our rewards, like our reward model in reinforcement learning, sort of rewards complete sentences. And we need a way to gather intermediate rewards. Like the problem is if we look at full sentences, the space of these sentences is very sparse. Like you're not going to see a lot of examples of a certain sentence in the English language. It's like the n-gram problem, right? Once you condition on like 9 words, like you've never seen like a sentence like that in your entire corpus. Like you've never seen a sentence like that in your life. Um, so essentially, the way that we can go here is either with a method called Monte Carlo, which always just translates to sampling, where we sample a bunch of potential trajectories, like a bunch of potential sentences, and we use that to sort of attempt to quantify how good of a reward is. This is like, because we're averaging a bunch of future trajectories, this has very low bias. Like we can expect on average to like not lean one way or another, but it has really high variance because our space is so sparse. There's so few sentences that like align with a certain reward, and our reward is so far in the future that we'll very rarely essentially get good signal, and ultimately our reward signal can be all over the place. So the way people address this is by distributing reward on the token level. You generate a token and you get some reward. Like you generated, like you started with the sentence I like, you generated pizza, you get a reward for pizza, like immediately. Or you, instead of a sentence, you could generate 3 words at a time. You could say I like, and the next 3 words are pizza very much. And you get a reward for those 3 words. And essentially what you end up with is now you have to find a way to assign rewards for incomplete sentences. And that's where the critic comes in. The critic is a method that assigns rewards for incomplete sentences. It attempts to predict how good your sentence will be given you just generated those 3 words. So the what I put next to the actor is just the advantage function because that's what the actor is trying to maximize. And what I put next to the critic is like the function that the critic is trying to maximize, which is it's trying to predict given ST, which is a temporary state, it's trying to predict the reward over the full sentence, which is like given with S capital T. And R is a reward. So again, what we're trying to do is we're trying to use some temporary state to predict reward over the full sentence. Does this make sense to everyone? Okay. I will assume again that if I don't make sense, I'll be interrupted. Now, this leads us to something called general advantage estimation. What general advantage estimation is precisely what we just talked about. We're going to take a trajectory of k words, like k, the next k words. And for each of these k words, we're going to predict a reward with our critic model. Like we're going to try to predict how good that word is using our critic model. And then our total advantage is essentially going to be based on the total reward we accumulate on from our critic model, given we just generated these words. So PPO is very much based on these things. Do not forget that the critics objective is to maximize like using its temporary state the prediction over the full sentence, and that the advantage function is just let's predict the next few words better than random, or as much better than random as possible. Now, this lambda is going to be a discount factor. So, like current predicting a word, one word into the future, may be super important to us, but like maybe predicting 40 words into the future, that's like a much noisier task. And we don't really know how much we should value that. So lambda is sort of this exponentially decreasing thing. You can think of if lambda was 0.5, the first reward would be weighted at 0, 0.5, delta 1, and delta 2 would already be weighted at 0.25. So it goes down exponentially. The last thing I want to say is lambda sort of toggles between bias and variance. If lambda equals 1, you sort of get like the exact like Monte Carlo sequence here. You sort of sample an entire sentence and give each word equal probability. If lambda equals 0, you're basing everything on the next token, um, and which is lower variance but might have much higher bias. Um, Basically, general advantage estimation is a way of estimating how much better we are than random. Okay, now we're going to get to PPO. And the reason I'm explaining what PPO is, even though it's not what they used, is because it's what they improved upon. And once I explain this, it will become very evident why what they did is simpler and better.
Yo, Gil, real quick.
Yeah,
How many slides do we got in this?
like 20, but they get increasingly faster.
Okay, word, got it.
Yes, I figured I would spend a lot of time on this. Would you guys say I'm going too slow? I tried to make this like very clear.
I would say it depends on like the background knowledge that people have,
I think
but
it's okay.
good.
I think, like, to be honest, if someone has no background knowledge, they're not going to understand it either way. So, like, whatever. I think you're fine. What time is the presentation supposed to end? Like, approximately.
I think I'm gonna finish like 9:30 or before.
Okay, great.
Um, Now there's a few more objectives here, like that PPO is trying to maximize because it's trying to maximize a few things at the same time. This H data is essentially an entropy function. Entropy means like how different you are from the initial distribution of what you were trying to maximize. So like let's say you're optimizing a model and it starts like generating words like elephant, right? And you go from like generating words like elephant to generating words like eraser, right? So that's a wildly different word. And that's essentially like a function of entropy. Essentially, what you have is a wildly different generation. So this encourages exploration. It encourages generating things that are different from the starting model. Then you have this clipped objective. And this clipped objective does kind of the exact opposite of or not the exact opposite, but something sort of similar. You see this advantage term in here, and it's trying to maximize it. So we're still maximizing advantage. We're still maximizing how much better we are than the random sequence, but it's clipped. So what that means is like if 1 plus epsilon was like 0.3, we couldn't we couldn't be better than we couldn't increase our value more than 1.3 times the advantage function. So the reason for doing this is essentially to avoid taking steps that are too big and leaving our local optima and optimization space. As the CT of pi theta, by the way, is the ratio of the new probability assigned to the old probability assigned. So let's say the new probability assigned was 19 times higher than the old probability, right? Then if we had no other terms in this function, we would just multiply by 19 times the advantage, and we could use that as our gradient descent update. But because we have this 1 minus epsilon and 1 plus epsilon times um, this ratio, we essentially really constrain, and we're taking a minimum over these things. We really constrain how big of an update we can make. The KL divergence is sort of minimizing divergence from the old model, and we are simultaneously optimizing the critic here. So those are all the things that we're trying to optimize. We're trying to optimize like four objectives at the same time. Things it works, and this works very well because it's kind of maximizing all the right things, but it's quite complicated. And they found something that worked better and was simpler. So GRPO takes like two of these objectives and kind of throws them in the garbage can. And the main thing that it throws in the garbage can is the critic. So what GRPO stands for is group relative policy optimization. The reason the words group relative are there is because it samples a bunch of sentences. Let's say it'll sample like 1,000 sentences or 1,000 trajectories of sentences. And then it will compare the current sentence to all the other sentences it saw. Because you actually sample a full sentence, you no longer need a critic model. You get a reward at the end of the sentence. That critic model for predicting what your reward will be is no longer useful or necessary. So you can throw the critic model into the trash. And then what you do is you just like do this classic z-score thing of checking how much better your current sentence is than the average sentence you sampled. And based on that, determine your advantage function. So it's actually like a much simpler thing because you can avoid training a critic model, which is like clunky and could induce a lot of reward hacking. Um, you can avoid training this clunky critic model. You have this advantage function just given to you by sampling. And now all you're doing is once again maximizing this clipped advantage function, this advantage function that's just not allowed to make too large of steps, and also minimizing divergence from the initial distribution. Now, the one's question might be like, where did the entropy go? Like, why don't we need to sort of like optimize exploration? And what they claim is by like sampling a bunch of sentences, you kind of already are optimizing exploration in a sense. Okay. Um, See, there's comments. I'm gonna, okay. Um, yeah, okay. Um, Now the second part, I'm gonna start moving faster because it's less mathematical and more just here's what they did. So they have a training pipeline where they alternate supervised fine tuning, which like is just regular like supervised learning, and this GRPO thing that we just talked about for usually reasoning tasks. they kind of really separate their supervised fine-tuning from their GRPO in the paper. And they keep claiming they're like the GRPO is there for the long reasoning things because reinforcement learning can see rewards that are very far away. While the supervised fine-tuning was for other things, like other types of examples. But in reality, like the word that you keep seeing throughout this paper is like long chain of thought, reasoning examples, and those are present both in the supervised fine-tuning stage and the GRPO. So ultimately, what you see from this model is that they kind of really optimize for reasoning across all stages of this pipeline, which is why this model is actually much less general than their like normal LLM, which is just DeepSeek V3, and actually fails at a number of tasks that DeepSeek V3 does very well at, like JSON outputs and multi-step reasoning or multi-turn like role play and like stuff like that. So what they're doing is they're just specializing the living shit out of this model. And we're going to go into every stage of this pipeline. The first step, they take a bunch of, they call this like their cold start training. They take a bunch of chain of thought data that they generate, which is, I wrote model prompted here, but it really well, like it easily could be model stolen because they don't say which model they prompted from. In all other stages, they're like, we prompted from our own model. But here it's like very possible that they just prompted OpenAI, which is also backed by the fact that like when you ask DeepSeek what it was, like very oftentimes it would be like, I'm OpenAI, produced by OpenAI researchers. Um, so they prompted model and then they did the most brute force thing possible and like human combed through these prompts and made sure that they were good. So there's a lot of manual effort in this pipeline. And this is on the order of like a few thousand examples. So it's doable to look through them individually. Part two, they did this GRPO thing that we talked about for these for like two types of tasks. Um, it's like essentially, or let me restate, two types of objectives. At first, they tried just using verifiable reasoning examples, which are basically like I did a math problem. Did I get it right or wrong? I wrote an answer to a science question. Is it technically correct or not? They have very hard-coded answers to this, and this is like reserved explicitly for verifiable things like math and code. Then they noticed that if there was multiple languages in the prompt, or even in many random cases, DeepSeek would switch from English to Chinese repeatedly throughout the generation, and its reasoning would make no sense to either group of speakers. And they thought wisely that this was a problem. So they essentially introduced a language consistency reward, which kind of is the target language of the task kept throughout the entirety of the response? And essentially, if a model in any token generation strayed from this objective, it would be penalized. Now, you might see that there was like another stage here, but this is just a checkpoint, meaning like they just saved the model there. And here is like their second stage of supervised fine-tuning. This is where like they actually started to do something that was like a little more sophisticated than their initial stage. They took 600,000 reasoning samples and 200,000 others, but I put others in quotations because they're like, we still use chain of thought reasoning here, and we still used like these, we still try to elongate responses. And it's very unclear to me, at least, how chain of thought differs from reasoning, even though they use them very distinctly. I wasn't exactly sure why chain of thought wasn't reasoning. So they use these reasoning and non-reasoning quote unquote samples and essentially train again using, but in order to achieve all of these samples, they use their like base language model, like DeepSeek V3, to do rejection sampling. And they reject a bunch of samples that are shit, and they end up with like these 800,000 samples. The 600,000, I think, were probably generated. The 200,000, they said straight up, we copied this from the training data for our previous model and just kind of refined it. So the 200,000 samples are from their previous pipeline. The 600,000 are very much generate and discard if DeepSeek V3 thinks it's no good. Um, the last stage of this is their second state of GRPO. And that is like basically you can translate that in your head to RLHF. What it does is they take two objectives, which are healthfulness and harmlessness. I think this is very much based on a reward model because it's impossible to evaluate healthfulness and harmlessness without like humans annotating a bunch of shit. So humans annotate a lot, and you get this reward model that essentially says this is helpful, this is not helpful, this is harmful, this is not harmful. The helpfulness metric is applied to the summary that DeepSeek generates at the end of its reasoning. So DeepSeek was essentially built in a way that it puts its thoughts between thinking tags. You can think of these HTML tags that's like thinking, 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 answer. It thinks, it answers, and then it summarizes. So the summary was optimized for helpfulness with this RLHF step. But the entire thinking process, end to end, was optimized for harmlessness, which is essentially meaning like, did the model say something about like generating like a recipe for a bomb? Did the model like tell someone to do something that wasn't good? And you have this end-to-end formula. I'm gonna get a little more technical here one more time, um, which is the R1 architecture. Like R1 is a training pipeline. It's not an architecture. The architecture is DeepSeek V3. They have this architecture as a base, and this is the architecture where like the real innovations were made. And then they applied like a simpler RL thing on top of it that kind of worked, did some like what I'll call engineering tricks on top of it, and came up with a model that was like extremely good for a specialized set of tasks, but like keyword specialized. And they started with something that was already very good. Like DeepSeek V3 is a great model trained at a fraction of the cost. So I wanted to give you like a quick glance at like two cool things that DeepSeek V3 did that I thought were super interesting. The first is I'll turn your attention to this QKV equations over here. So the QKV comes from query key value, um, which is from our beloved attention. Uh, I'm almost certain everyone here has heard of attention, but just in case you haven't, it's like a way to weight the tokens around you and combine them into some meaningful embedding. Um, and before this query key value, this KV cache, you would multiply the query by the like key value multiplication. This KV cache was like prohibitively memory consuming. So you had this like massive KV cache that would assume like a very large amount of memory, which constrained inference on a GPU because it constrains like the number of like inferences you can do at a time. It constrains like the size of the model you can fit on a single GPU. And as a result, is a problematic thing for training and a particularly problematic thing for inference. So what they do is they do something that a lot of like people have been doing for years now, which is project things to a lower space. You basically multiply by a matrix that converts you to a lower dimension. So you have like this WAK, which is a mapping to some really low dimension R. And you reduce the dimension of what you store. And you only need, because like matrix multiplications are really cheap on GPUs, you you kind of can afford to do that second multiplication to return the matrix back to the normal dimension you use. Like that's not a problem to do that second multiplication. But all you need for storage, for that temporary storage, is that x times WAK or x times WAV, which is after multiplication, a much lower dimensional matrix that you're storing. Um, and this was an innovation that they claim reduced the size of their key value caches by 14% and significantly improved both their ability to train and do inference. The other thing they do here is something called multi-token prediction. So right now, one of the biggest problems, particularly in inference, is that you can only output one token at a time. The problem if you don't output one token at a time, which people have tried before, right, is then you can't base your next word off of the word you just generated. So let's say I'm using the sentence, I like timers as for the heck of it as an example. If the word like doesn't appear before timers, and I don't know that I'm about to predict the word like, timers becomes a much less likely word to follow up. I guess it wasn't a likely word to follow up in the first place, but if the word like isn't there, like it could be the word like am, and then I am timers makes no sense, right? So ultimately, what you have there is like a really big problem where if you use these parallel attention heads to predict simultaneously, it's hard to condition on things that might come before. So DeepSeek takes an intermediate approach. They don't predict a bunch of tokens at a time, they predict two tokens at a time, which still significantly improves their output. And what they do is, let's say the words um, I like are the first two words in the sentence. And then essentially what will happen is one attention head will just predict the next token very normally. The other attention head won't receive the sequence I like. It'll receive like I like some predicted token here. It'll have like a placeholder to say that there's some token that was predicted before you so that the next prediction could factor that into account. And then it allows the model to predict the next token. So this V3, DeepSeek V3 predicts two tokens at a time. And maybe to the words I like, ramen might be predicted as one word, and noodles might be predicted as the next because it conditioned on the fact that a word like ramen could have come before. Other than that, like the super high level is they do this multi-headed latent attention, which is what I just talked about, like the reduction of the size of the KV cache by projecting to a lower dimensional space. They do this MTP multi-token prediction. They have a really small gating model that routes like predictions to their mixture of experts. Like it routes the question at hand to the relevant expert. And those are essentially the big three of this model. Everything else is kind of, it might be important, but I think definitely for the most part more hardware centric. Okay, how do they do? This is my obligatory inclusion. On a very like hand-selected set of benchmarks, they do really well. Like really well as in like comparable to O1 and occasionally even slightly better. It's um it's actually pretty interesting because Deepseek R1 outperforms Deepseek V3 on almost everything in these among these reasoning benchmarks, except for like the Chinese simple question answering. And they said that the reason for that is like because of its like reinforcement learning with human feedback, it marked too many things as harmful and just refused to answer like Chinese simple questions. So I guess it was like kind of biased against these like factual questions in Chinese, which is quite surprising. But for the most part, it does well. And it does well with like a very small number of activated parameters, and it beats like models that might be larger, but we don't know because no one releases anything anymore. Now, the last really cool thing that they do here is I actually think this is the coolest part of this paper, and I found this to be like totally fascinating, is they take these tiny models like Quen 1.5 billion, Quen 7 billion, like models that like can do stuff, but not complex reasoning benchmarks. Like these are not models that should be performing on like Math 500 or AIM, which are like relatively complicated math problems. Um, and they take these models and when they just distill using like outputs from R1, which basically means they just train these models to emulate outputs from their R1 model, to just copy them. The performance skyrockets like crazy. And you can look at like Quen 32 billion is not the same as QWQ 32 billion preview. It's like a much worse model. Like QWQ is supposed to be way better. And we're seeing like a 22.6% increase for pass out one on like really tough American math problems. Um, and an improvement over models like Claude 3 Sonnet, 3.5 Sonnet, which is nuts when you think about the size of these models. And these are dense models too. So it's not like there's 8 billion parameters active. No, like in Llama 8B, 8 billion parameters is all there is. So yeah, it's actually quite impressive and I think shows that if you have like a really good base model, you can take these tiny models that might be inferenceable on like a few GPUs and get like really good results on a bunch of specialized tasks. Now, they claim that there were things that didn't work. Um, Process reward models was one of the things that they really ranted about. There was like a half-page rant in the middle of their paper about how much process reward models suck. They said that it was like really hard to define. By the way, a process reward model like is what it sounds like. It rewards intermediate steps in a process. Basically, like if I'm thinking through like x squared equals 9, and I think, oh, this is a quadratic problem. I should take the square root of both sides. Like the solution will have like a plus minus on one side. It's like the square root of 9 is like plus or minus 3. Like you take this set of reasoning steps and you reward each one of them to ensure it's along the right track. And they're like, this didn't work for us at all. It was hard to define steps for a lot of their problems. It was really difficult to generate automatic annotations for them. They find that like modern language models were bad at grading steps and they really didn't want to do anything by hand, which I don't blame them for because their company employs like 200 people and like training this model must have already been really hard. And when they do train these models, like you get these reward hacking problems where like the models learn to reproduce intermediate steps without reaching the final destination. Like They get a lot of reward from reaching intermediate steps, but essentially gain sufficient reward and don't continue to the correct answer. They also try Monte Carlo tree search, which is like an algorithm where you like balance exploration and exploitation, and you search a bunch of possibilities as you're generating an output in a smart way using some value model that like tells you what to search. And they said that training the value model was really clunky, that it introduced like an additional training step that they couldn't optimize well. And they said like relative to their resources, this just didn't work. They also very nicely provide their limitations. The model still, despite their language consistency objective, randomly spits output in English and Chinese combined, as I'm sure we might have seen from playing with it. Um, this was actually really interesting to me. Providing the model examples, few shot prompting, like consistently made performance worse. And they reported it and they're like, for best use, please don't give the model examples, which I found to be absolutely hilarious. And I found it to be very interesting. And as I mentioned earlier, it's a very, like, not very specialized, but it's reasoning specialized model and underperforms V3 in certain tasks. So it's not like a strictly better next gen model. It's just like a more specialized model on top of something that was already really good. Um, Now we're gonna get to the fun part. I only have a few slides left, but I wanted to talk about DeepSeek a little bit. And all of the information that I'm going to give you here can be found from two sources. It's like the semi-analysis report on them and Dario Amadei's blog post ranting about why we're exporting too many GPUs to China. DeepSeek is the AI arm of a hedge fund called Highflyer. Highflyer is a fund with $8 billion in assets, and they're basically the OG AI quants. Like they started using neural networks to trade like way back in 2016. And before like the first GPU restriction on A100 took place in, I believe it was 2022. Someone can correct me if I'm wrong. In 2021, they bought 10,000 A100s. So even if DeepSeek like might claim that they don't have access to A100s, they kind of do because DeepSeek and Highflyer very often share resources. They're sort of run by the same CEO, and they have plenty of they have actually have quite a big compute cluster. Highflyer is they spent like many millions of dollars on their compute clusters and actually retired their first one because it wasn't performant enough. Um, Essentially, everyone has sort of gone crazy about DeepSeek because everyone claims that they trained a model for $6 million, while like these giant companies like OpenAI and Anthropic train their models for billions. So they're like, how can a Chinese company come in, train something for like 1/160th of the cost, while we pay like crazy for NVIDIA GPUs, and suddenly NVIDIA stock drops and everyone goes crazy and um all the rest. So I wanted to give you like a quick follow through of the money involved in the situation. The $6 million was the cost of the pre-training run. That's just the cost of like, here's a bunch of inputs, here's a bunch of outputs, emulate that. Semi-analysis claims that they spent approximately between Highflyer and DeepSeek $500 million building their compute infrastructure. They spend a lot more on salaries. Some of their salaries are as competitive as $1.3 million a year, which is much better than any other um, Chinese AI startup or hedge fund pays. They spend a lot on hardware maintenance, and as most like research companies do, they run experiments before they go on their like YOLO training run. Before they like commit all of their resources to training this giant model, They still run a bunch of experiments, and those experiments take money. It costs money. Basically, like we're not talking about like a $6 million investment in DeepSeek V3 or in DeepSeek R1. We're talking about like one part of the restaurant bill. Like you go to the restaurant bill to the restaurant and you order like the chicken, a steak, and a lobster. And like the chicken cost the $6 million. We're talking about a very small part of the cost here. There's a CEO who has like essentially been like an AI trader since college. His name is Liang Wenfeng. He's like basically starting to be known as like a Chinese Elon Musk. He's 40. He owns like 86% of DeepSeek through like two shell corporations, and I think like 72% of high flyers. So he's very, very much in command of these companies. So the question is should we panic? Like, did DeepSeek do something extraordinary? Well, the answer is yes and no, right? They had a lot of GPUs that weren't A100s, that weren't like as good as the ones American companies train on, and they still achieved like something remarkable by like essentially a really, really massive plethora of hardware hacks. Their pre-training run was $6 million, which like relative to Anthropic, Dario Amodei said his pre-training run for Claude like 9 months ago was a few tens of millions of dollars. So like we might have lowered the cost by 5x. That like that's a possible thing, but it's not as large of a jump as one might believe. And if you can see like every year, the cost of achieving a certain performance on MMLU goes down like 4x. So it's like kind of a consistent scaling law. It's like almost like the new Amdahl's law where the cost of like achieving a certain performance for per a certain number of tokens goes down like 4x every year. And it's been like that since like essentially ChatGPT was released. There's like an earlier version of this chart that shows the same trend. Um, and I'm talking about the chart on the right here, which like essentially estimates the cost of reaching a certain MLU performance. So essentially, DeepSeek was like the next part of this process. They made like maybe a slightly larger jump than the median jump in this process, and they got there first. But this has been like a consistent trend. This is not some exponential increase in the capabilities of language models. Um, in addition to this, like DeepSeek R1 is not as unbelievable as one might think. We were led to believe that DeepSeek R1 was essentially like the either the leading language model or identical to O1. Results show that that's not really true. In a like this is from I think an intelligence like artificial analysis. It's an intelligence tracking site, and you can see that like R1 still lags behind like five OpenAI models. It's nowhere near O3. And even if you look at benchmarks relative to O1, it still falls short in many categories. O1 is still a better model. DeepSeek R1 just got close in many ways. So I think there's no reason to panic. Bottom line, they did something really cool at a fraction of the cost, but not like 1/160th, more along the lines of like 1/4 or 1/5. And they're a very good model that's up there, but not the best that humanity has available. Um, and that will be it for me. These are my references. Does anyone have any questions or that wasn't mentioned here? Is the DeepSeek engineers? Yeah, they did. They did do that. All
Oh
right.
yeah, I have a question about that. Like, you're talking about the Dario Amodei article. So he's like CEO of Anthropic, right?
Yes.
Okay. Do you think I don't know anything about like Dario Amodei or like how like good his articles are. You probably know a lot more about this. So like, I don't know. Whenever like Sam Altman talks about like um I don't know, like or like big tech CEOs talk about like, oh, we should like regulate more, or in this case, like export controls. Like, do you think he's biased by, I don't know, like shutting down competition, like that kind of thing, or would you take his article like at face value?
I think you make a very good point. I definitely think that he doesn't want competition coming from China. I think that's definitely like a problematic thing. At the same time, I think holistically maintaining some US edge is something that a lot of like big tech CEOs and Americans seem to align with. Um, so it might have been his pre-existing belief, but I would say it's definitely exacerbated by the fact that no one wants to be up against a Chinese company that's like literally going into CUDA and modifying CUDA code like custom to optimize the living heck out of their runs.
Okay, yeah, makes sense. Makes sense.
Any any other comments, questions, something someone wants to say?
Thought it was a great talk, Gil.
Yeah.
Good
I
shit, dude.
Thank you. I hope this was helpful, and I'll try to do this more. I think in the future I'll probably try this more along the lines of a discussion about a topic. I think that's another thing I've been really wanting to try. But I hope this was helpful to people. And if you have any questions, you can always text me, or if you have any ideas that you want to bring up. Like I definitely don't know everything about this stuff, so I appreciate any insight and things of the sort.
Yeah, no, I like this idea. I definitely think agree like more discussion based next time might be good. Or in person possibly.
I think we could try in person. I I think the
Get a communal pot of coffee and start ripping with a whiteboard nearby.
I
That'd be
think
cool, yeah. We could like book a room.
that's true. I think like one thing that might be really interesting that Alon actually suggested is like having people like mutually discuss research. Like everyone kind of explains what ideas they've thought about in the past, and we all kind of like riff on them.
Hmm. I think that's also a good idea because I mean we are a lot of us in this group too are like doing our own research too. So we have like different perspectives to come at it. I think that's probably like a very productive use of time.